Good morning, everyone. I hope you can hear me. Today, we are going to have lecture number 4.2 and 4.3. Today is 5th October 2020. So, what we are going to learn today is that we are going to learn about HM. HM is maximum uncut chip thickness, or it is the maximum grid depth of cut. By whichever name you call it, you can use it. Maximum grid depth of cut is kind of a legacy name, whereas maximum uncut chip thickness is a name which can be used across grinding, machining and everything. So this is the chip load. This one is the chip load in grinding per grit for a given grit, and this is being extracted from this particular figure. As you can see, this is the feed, this is displacement of the workpiece per abrasive particle or grit. It is very similar to millimeter per tooth. This is the starting point of a particular abrasive particle, and it leaves the cutting zone at this particular point A star, and instead of following AB, it kinematically follows this because of this VW, and this is rotating in this direction with NS, which gives rise to the surface velocity of Vs. Now our interest is to find out an expression of HM which is a function of process and geometric parameters of grinding. You might say, why we are doing it? That answer is embedded in its name. Its name is uncut chip thickness or maximum uncut chip thickness. That means this will control chip load. So if we can characterize chip load, we would be also able to characterize forces in grinding, provided we know how to determine HM. So that is our task. For doing that, first and foremost, what we need to do is to look at the abrasive, the shape of the abrasive. So what is the shape of the abrasive? It is irregular. However, it has ridges like this. Second thing, we know that they provide a statistical negative depth, negative rake of minus 60 degree. Based on that, if I put a parting line here, the lower part of the abrasive can be considered as a square pyramid. This is an approximation, but this approximation we will be using. This square pyramid is having an apex angle of 120 degree. So the angle between this particular face and this particular face is 120 degree. This is taken as 120 degree because my statistical average rake angle is minus 60 degree. To take for that, so this is minus 60 degree and this is also minus 60 degree or 60 degree. In that particular case, the apex angle has been taken as 120 degree. So this is the model shape of an abrasive. This is not a normal, this is not the actual abrasive. Actual abrasive is irregular. From this particular fundamental observation that rake angle is minus 60, to get a mathematical value of it, to analyze it, to model it, we have taken it as a square pyramid apex space. Now how the chip group looks like. So for that we need to draw both the machined surface and unmachined surface. So this is your transient surface, this is your ground surface, this is your unground surface. This we have shown you earlier, and let us assume a particular grid is starting, only one grid is starting to make chip formation. That chip groove would look like this. Why it would look like this? Because as it progresses in this particular direction, because of VW, gradually the instantaneous chip thickness would increase. So this is your HI. HI is instantaneous uncut chip thickness. That would increase. Why would I have this kind of shape? This kind of shape will come. This kind of shape means gradually the width is increasing. That will come because I have assumed my grid to be having a pyramidal shape. So this would be the chip groove. So if I draw it separately, this would be the chip groove. This surface is on the unground surface. This particular plane which is here, this particular plane is on a plane which is a vertical plane. So this portion from this vertical plane to the unground surface, this is very small in size, and for our modeling purpose we would not consider this. So if you go back to the previous diagram, where is your point B? Your point B is here. So let us not give that same nomenclature. We will say this is point A, this is point B, this is point C, this is D, and if you drop a perpendicular, this becomes E. And your BE is your HM, that is maximum uncut chip thickness or maximum grid depth of cut. And AB for all practical purpose is LC. One can say that this B has to be extended this particular point. I fully accept that, but as I said, beyond this vertical plane, this particular portion is very small in size and that much approximation can be made. There is one more thing. What is CD? CD is the width of the chip groove. So CD is the width of the chip groove, and for that this is the maximum width, so we will use BM. If you characterize chip groove somewhere else, we will simply use BC, that is width of the chip groove, but at the maximum plane where HI is becoming HM, we will call it as maximum width of the chip groove. So this is the shape that we have to use, and with this shape we will try to see whether we can characterize the chip volume or not. So once again, let me draw it. So this is A, B, C and D. Now if you go back, this angle theta, which was calculated in the last class as cos I equal to 1 minus 2a by ds, this theta is very small. This is very small. As because it is small, we can assume that this arc length AB is almost like a straight line. If I assume it to be almost like a straight line, now here comes the tricky part. This becomes A, this becomes B. The dotted line I am drawing because drawing a straight line continuous is rather difficult, so I am drawing a dotted line. No other significance. So this point is C, this point is D, and if you drop a perpendicular here, this becomes your E. Where is that E in the previous diagram? E was here. So this was a perpendicular dropped on this. The rest of the part, that means from this vertical plane to this particular plane, whatever chip groove is there, that we are not considering. So if that is the case, what are the assumptions? The assumptions are angle DBC is equal to 120 degree, or it is equal to the apex angle of the abrasive. Why is it so? Because the abrasive has generated this particular chip groove. What is the other observation? AB is equal to LC, PE equal to HM, and CD is equal to PM, and DE is equal to EC equal to half CD. So these are the observations which we can have from this. So what is this? This chip groove is more like a triangular base pyramid. How can I say this is a triangular base pyramid? Because the angle subtended by contact length at the center, that is very small. Angle subtended by contact length is very small, and that you can numerically calculate by using the formula that I have shown you some time back. Where did I? Yes, this particular formula. Cos theta equal to 1 minus 2a minus 1 minus 2a by ds. Now, how can I calculate the volume of this chip groove? This is a triangular pyramid, triangular base pyramid. Volume of the chip groove, this is capital gamma chip groove, is 1/3 into area of the base into height. So how much is my height? That is straightforward, LC. And how much is the area of the base? Half PE into CD. So that becomes 1/3 LC into half HM into BM. Now if you say this angle is 60 degree alpha, so tan alpha is equal to D by B, which is Bm by 2 by Hm. So from that it comes out to be 1/3 LC Hm square tan alpha. What is alpha? Alpha is the half apex angle of that abrasive, which happens to be numerically equal to 60 degree. So we have got an expression for chip groove. From this we need to find out how we can calculate this HM value. Why we need to calculate HM value? Because if we can calculate HM value, our proposition was that we would be able to calculate forces, specific grinding energy and other things, and we would be able to relate them. So let us see what we can do. So what we have achieved thus far? Thus far we have achieved an expression of chip groove. What are the assumptions? The assumptions are, we have approximated a irregular grid like the half of the irregular grid which interacts and forms chip. We have approximated that by a square base pyramid having an apex angle of 120 degree. Why 120 degree? Because the abrasive grids, they pose a rake angle of minus 60 degree. This is one particular assumption. Other assumption is that this arc length BC is almost like a straight line because angle theta is very small. So the chip groove almost looks like a upright pyramid having a triangular base, and from that upright pyramid we get this particular expression. Now can we use this expression to calculate HM? And for doing that we will equate local material removal rate with global material removal rate. What is local material removal rate? We have not defined. For plunge surface grinding case, this is our case that we will use for all modeling. We know my material removal rate that we know is VW A into BW. This we are trying to equate with something. What we will equate with? So what is this? What is this quantity? LC into BW. If we go back, no, I'll not go back, I'll redraw it here. So this is my width of the job BW, and this length from this point to this point, this is LC. So LC into BW is the area of the grinding zone. More commonly it is called contact area. So that's what we are going to do. So contact area, and that we are multiplying by a term called C. What is this C? This C is called grid density, and it is calculated as number of grids per unit area. So it is, say, 50 grids. This is a numerical example per millimeter square. See, it is something like this. After some time we'll introduce two concepts. One is static grid density, another one is dynamic grid density. For the time being, let us assume that it is simply known as grid density. So if you do this, what do you get? What is this quantity? This is total number of grids on the contact area. Now, just a small question so that you do not go to sleep. What is this, by the way? This particular expression we will not be using, but what is this? Can any one of you tell me? Please unmute yourself and tell me what is this thing. So you need to look at this and that you are multiplying by grid density. What would you get? Who can answer this? Please give me a wrong answer. At least give me an answer. Please do not keep mum.
Cutting speed of abrasive particles.
Slowly. Please speak loudly and slowly. What is your name, son?
Murali, sir.
Murli. Yeah. What is it? What is pi ds into bs? First, let us concentrate on this particular quantity.
I think cutting speed of abrasive particle.
No. Pi ds into bs. This is a distance unit. This is also a distance unit. This is width of the grinding wheel. This is the diameter of the grinding wheel. So this is basically an area. What area is this? Murali, can you tell, or anyone can help Murali?
Sir, it is number of grids.
No. What is pi ds into bs? First tell me that.
Sir, it is area.
Which area?
Circumference into width.
So it is the peripheral area of the grinding wheel. If you stop, please. This is my grinding wheel. This is this peripheral area, which on the other side also it is there, which I cannot see. So this is the peripheral area. Very good. Who was it? Who was responding to me?
Gajanan. Sir.
Gajanan. And that you are multiplying with by C. So what do you get?
Number of grids.
Total number of grids on the complete periphery of the grinding wheel. That we are not using. We are using LC into BW into C. Very good. Very nice. Now let us see how we can modify the statement that we have written at the top. For that, I will be using some other color. Okay. Now what I am doing, then what is this quantity? This is chip groove of a single chip, and this is number of grids which are present on this. So if you multiply, what do you get? You get amount of material removed by all the grids on the grinding zone. Now I am dividing that by a number. What is that number? So first, any one of you, can you tell me what is this number? Any one of you, can you tell me what is this number? What is there in the numerator and what is there in the denominator?
It is time of engagement.
Whenever you respond, as because this is not a 1:1 class in a classroom, I cannot get to see you because I do not have multiple monitors so that I can engage that. So please respond. Whenever you respond, you are responding very kind of you. Please tell your name first.
This is Durganand, sir.
Durganand. Yes, very good. So what is LC, son?
LC, length of the engagement.
It is the
Length of the engagement.
length of the engagement. The technical term for that is contact length, and that you are dividing by Vs. So what is this term? What I have put an asterisk here. You are saying something. You are going in the correct direction. Come again.
Time of engagement, sir.
Time of engagement. That means a grid starts cutting from this particular position and it disengages over here and it moves over a length of Vc. With what speed does it move? it moves with a speed of Vs, that is the grinding speed. You might say, depending on whether it is up grinding or down grinding, it should be corrected by this, but depending by comparing the value of VW with Vs, if you simply write it as Vs, you do not make lot of problem, you do not create any problem. So what was this, which is, let us give a symbol like this, and what is this? So this is time of chip formation, and what is this? The amount of grid chips, the total volume of the chip produced by the grids which are active on the cutting area. So if you divide the total volume divided by the area, time required to produce that, what you get is the material removal rate. So what I am terming this as is the global material removal rate, and what I am terming this that is the local material removal rate. For local material removal, what have I done? Volume of one chip into number of chips divided by time. This is what I have done. So volume of one chip is nothing but this, number of chips is this contact area into LC, and time required to form the chip is LC by Vs. This is what we have done. I do not know whether I have space in the next slide or not. I do not. So I have to create space. So please bear with me so that this can be taken forward. No, not this one. Good God. Okay. So here I have a free slide, so I have some space. So what we wrote is something like this. VW A into BW is equal to chip volume. If I remember the chip volume correctly, it is 1/3 HM square tan alpha into LG times C into, okay, let us not use LG, let us use LC. I have a bad habit of interchanging symbols. So this is LC, this is LC into BW, that divided by LC by Vs. So as because there is a division here, this LC and this LC will cancel out, and we will get 1/3 HM square tan alpha C Vs. This Vs will come in the numerator into LC, and instead of LC I will write A into DS. You might say, why are you writing DS? Because I am doing it for surface grinding. If you are doing it for if you are doing it for cylindrical grinding, DS would be replaced by DE, which is the equivalent diameter that we have discussed in the last class. So this is equal to VW A into BW. Now things will start cancelling out. Oh, there was one BW that I have missed. So this BW was there. So this BW and this BW will vanish, and HM square would become, these three will go to the other side. This C tan alpha will come here. This VW remains here. So this is VW by, and this Vs comes over here. This A will interact with this and give you a form like A by ds. So HM, which is called uncut, maximum uncut chip thickness or maximum grid depth of cut, that becomes 3 by C tan alpha into VW by Vs into root over ADS, whole thing under root. if you try to do a dimensional balance, this is a non-dimensional number. It is a ratio of two speeds or velocities. This is a non-dimensional number. This is a ratio of downfeed by ds. This is C. C is having a dimension of grit per millimeter square. So that per millimeter square goes to the top and that to the power half. So HM comes out in millimeter provided C is in grit per millimeter square. So this is the expression of HM, and our proposition is, or my proposition was, if I can calculate HM, then possibly I would be able to correlate it with lot many things like forces, specific energy and all that. But first try to understand what is the size of the HM. For doing that, there is a slide afterwards, but I would not use that slide because before going there I will use some other slide. So please give me some time. Copy. Oh God. Fine. So this one I'll copy. Bring it here. Get rid of this. Bring it from here. I'll get rid of this. Okay. So now you have a problem and that you have to solve. It is a numerical problem. What are the things which are given? First thing is that we have derived the formula of HM. The formula of HM equal to this. What is this particular case? What has not been said is that this is a flange surface grinding. This is a case of flange surface grinding. Downfeed is 45 micron. DS is 200 millimeter. I am extracting things from there. Vs is 50 meter per second. VW, which is work speed, is 100 millimeter per second, and grid density is 20 grids per millimeter square. So let me take a rest. I am giving the lecture for a long time. So you people please calculate HM and give me HM. When you are calculating, please keep in mind it would be a very small number. It would be so small that you have to express it in micron. So let us try to get how much is HM. So take some time and please calculate HM and give me the value. Please take out your calculators. I do not have my calculator in this room. I have to bring it. So please help me in calculating HM. If you require help with alpha, alpha was half apex angle related to the abrasive, which is 60 degree. So we'll wait for 5 minutes and then You need to give me an answer. In the meantime, what I can do is, no, let you give me the answer. So what is the progress? Anyone?
Sir, 0.00279
What is the unit, son?
micrometer.
No. I'll note down the number that you have said, but that cannot be so small.
279.
279. This cannot be micrometer. Possibly this you have got in millimeter.
Yes, sir. I got 2.79 into 10 raised to minus 3.
2.79 into 10 to the power minus 3. So 2.79 micron. Now, anybody else? I would not proceed if I do not get confirmation from at least two of you. Who was it?
Gajanan.
Gajanan. Thank you, Gajanan. Anybody else? Gajanan, please mute yourself so that the rest of the guys can also participate.
Sir,
Yes, Muralidhar, I can see you.
Murali, I got 50.97 microns.
Okay. So let me document that. Come again. 15 point.
50.97.
50.97 micron. As you can understand very well, your uncut chip thickness is 45 micron. So your HM cannot be so large. Why is it so? Because from the drawing itself you can understand this is going to be your HM, where this is A, and this scale that we draw is exaggerated because this angle it is sustaining is around 60 degree, but actually this angle is hardly 1 degree or so. So this HM would be very less. So what I would suggest is that you recalculate. One thing is very good of you. It was Gajanan, that even when you have got an answer which you understood is not correct, despite that you have shared with us, very good of you. So I would request you to recalculate. What about others?
Sir, I have a doubt, sir, in that values.
Hmm.
VS is 50. Okay, sorry, sir.
VS is 50 meter per second, VW is 100 millimeter per second.
Okay.
Anybody else? Okay, I have got my calculator now, so let me try. So I would require help from you. So this is HM equal to, where is my pen? HM equal to 3 divided by C. C is 20 into tan 60 into VW. VW is 100 millimeter per second. To bring it in the same dimensions, it is 0.1 meter per second divided by 50 into root. So this is 0.045 divided by ds is how much? Ds is 200, and the whole thing is to the power 0.5. So if you calculate, you will get a number. Is there anybody else who can confirm this 2.79?
Sir, I got a different answer.
Okay,
Ankit
so let me do it. Let me try it. Okay, who was it who has got a different answer? It was Girish.
I got 2.4. Yes, sir.
Acha, Ashok More, how much you have got?
I got, sir, 2.497.
197. Okay, let me do a calculation. So it is 0.045 divided by 200. Whatever number is coming, I will take a square root of that into 0.1 divided by 50. Whatever is coming into 3 divided by 20 divided by tan 60 and square root of that. How do I get square root of this answer? Yes, this is it. I am getting even smaller number. So, is there anyone who is getting a number which is even smaller than that? Acha, Ashok More, you did get a number. What was that number? Can you tell me, please?
2.497.
497. Acha, anybody else?
Sir,
So Ankit,
I got
I got
2.7.
1.6.
1 point?
1.6, sir.
Who is it? Can you give the answer till third decimal place?
1.6118, sir. Kailash Raja.
Kailash Raja. I also got this number 1.8, 1.6118. So what I would not do today is that I will not bring up the calculator, online calculator. I cannot use it very nicely. But I do not know whether you can see this or not. Can you see this?
no sir.
Why can you not see?
Because it's blurring out, sir.
Oh, it is blurring out.
Yes, sir.
Okay. Oh God.
Sir, I got the same answer, sir. Vipul here.
Sir Ankit here. I also got the same answer.
Same answer means 1.6118.
Yes, sir.
Okay.
Yes.
So, but why this is blurring out? I don't understand. No, I would not be able to change it during taking class, so I'll keep it like this. So, what we will do is that we will okay. So, what we will do is we will erase everything. Why can I not get the eraser? Strange. Eraser is no longer available. So what I will do is that these are wrong. But once again, whoever has given me the first answer, even if it was wrong, I really appreciate. If people do not participate in the class, it becomes meaningless. So this is your HM. So now you can understand in grinding why it is such a small, why the size is so small. The size effect is there in grinding because HM, which is equivalent to A1 in machining, A1 is uncut chip thickness. So these two quantities are markedly different. If you are doing turning, your A1 could be very well 0.1 millimeter, which is 100 micron, where in case of grinding, you are getting a very small number HM. So how do I reduce HM? Can any one of you suggest something? I have not discussed it. But in front of your eyes, there is an expression for HM. Just look at that expression and tell me, how do I reduce HM? Mathematical, do not think about the practicalities.
Cut.
Mala Muralidhar, you are responding?
Increasing VS, sir.
Increasing VS. Okay, fine. That is a very good answer. So you increase VS. Anybody else? Give mathematical answer, nothing else. Reduce VW, reduce A, increase DS, increase C. Tan alpha cannot be touched because this comes from the geometry of the grid. How many of them are actually implementable, and how many of them, if you implement, leads to a technology? Can you reduce VW and A? Unfortunately, your material removal rate is VW into BW into A. So if you reduce them, your material removal rate will go down, which is not a good approach. DS, can you increase? Yes. But you cannot make DS equal to 2000 millimeter. That is too large. It is as tall as possibly the tallest guy in the class. I do not know who is tallest. I am definitely not 200 millimeter. I am much shorter than that. So there is a practical problem of increasing DS. So this is not a good solution. This is not a good solution. This is not a good solution. This is the most viable solution which was provided by Muralidhar, and this leads to a technology which is called high speed grinding. How else can you do? You increase C. How do you increase C? That will come after some time. Possibly within 2-3 slides, we'll come to that, how to increase C. Next point is, why should I try to reduce HM? I said you reduce HM. Why? Why should I do that? If you reduce HM, your chip load goes down. If your chip load goes down, your forces will go down. At this stage, you must understand which force we are talking about. Till now, as you know, there is a capital FT, tangential force, a capital Fn, normal force, and possibly I have introduced something which is capital AX, axial force in case of traverse grindings. These forces, would they come down? It is not so easy to speculate whether these forces will come down or not. Oh, I am not able to. Strange. Okay, so whether these forces will come down or not, we cannot speculate. So what forces will come down? Forces which are working on a single grid, they would definitely come down. If you say, if the forces on a single grid comes down, then what is the advantage? My problem, I was trying to give an example using some Sanskrit slokas, but I am very poor in Sanskrit. So whatever I understand from that sloka, I'll try to translate in Hindi. Please do not laugh at it. My Hindi is also very poor. It is something, there is a saying in Sanskrit, Bindu te Sindhu. Bindu te Sindhu is a Bengali word. That means from Bindu you get the Sindhu. Sindhu is the river or the sagar. So Bindu is a single point. So single grid forces are your Bindu. There is a nice technical term for that, which is called unit event. If you reduce the unit event of a manufacturing process, then your global accumulation of that would also come down. So this is a hypothesis. Say for example, in EDM, if you reduce the pulse energy, the size of a single crater will go down, you will get a smoother surface. Similarly in grinding, if you reduce the chip load, you will get a smoother surface, your force on a single grid will come down, so that is our Bindu or unit event, and that will lead to smaller global forces. Global forces are what? Which are acting during grinding. Which are FT and Fn. So what we can speculate, if you reduce HM, forces which are working on a single grid, they will come down, and from the hypothesis of unit event in manufacturing process, we can say forces, the global forces would also come down. So let us see the next point, and after that we will take a break. So already we have done the estimation of maximum grid depth of cut, and this has come out to be 1.612 micron with a C value of 20 grit per millimeter square. Who provided you 20? It was part of the problem. Now let us look at a 2D section of a grinding wheel. These are the grits. What can you control about the grits? You can control the size. Mesh size of a grit is 100. So DG is, so roughly, so is it 151 micron for everything? What is DG? DG is called average grid diameter. So there is a concept of variation of grid diameter. So if you can see, this is the grid diameter of one grid. This is one grid. This is one more grid. This is one more grid, and there is variation in grid diameter. Overall, they are more or less all similar, but there is variation. If there is variation, one of them would be protruded a bit more, one would be bit less. So because of that, if you count 1, 2, 3 and in this way you get a number, this many grids in this much millimeter square and get this number, that C is called static C. Then what is dynamic C? Dynamic C is the actual number of grids that participate in chip formation. When I say chip formation, it means grid chip interaction. So how do I get it? Is it a function of this? Yes. Unfortunately, C dynamic is a function of your process parameter as well. So how do you estimate at least C dynamic? For doing that, there was a very old technique which was proposed. For doing that, I need some space, so I cancel out everything. You take a glass plate. This is your glass plate. You put a coating of, very thin coating of carbon black, and then on this you roll your wheel. When you roll your wheel, this was your front view. After rolling your wheel, your glass plate would look like this. This is top view. These grids which are protruding more, which will participate in chip formation, they will remove the carbon black, and you can find out how many such points are there over 1 millimeter by 1 millimeter, and you can find out C dynamic. Is it the actual C dynamic? No, but it is the nominal value of C dynamic which you can use. C dynamic is always less than C static, and some of the researchers, they have given rule of thumb that how to calculate C dynamic. I will not go into that. So I'll stop now, and for the next part of the video I'll take a break. I'll take the attendance for the first part, and after that I will tell when we are going to reassemble. So we are going to keep it, we are going to save it. Where is my attendance sheet? This is my attendance sheet. Acha. Vinit Malik, are you present? Vinit Malik, are you present? I can see you. You are there in the meeting. Why don't you respond? Shiva Shankar?
Present, sir.
Thank you. Then is Kailash Raja?
Yes, sir. Present.
Vipul Kumar?
Yes, sir.
Thank you. Harsh? Harsh? He is absent. Arpit Patel?
Present, sir.
Shantanu? Shantanu? Oh, he is also absent. Ashok More?
Present, sir.
Ankit,
Present, sir.
Anup Kumar Singh,
Present, sir.
Muralidhar,
Present, sir.
Ritesh,
Yes, sir. Present.
Girish,
Present, sir.
Gajanan,
Present, sir.
Durganand,
Present, sir.
Rohitas,
Present, sir.
Sarjil,
Present, sir.
Vinit Malik, are you still there? To answer, you need to unmute yourself. Where is this guy? Okay, so at this stage, what we will do is that we will take a break. It is almost 10. We will reassemble at 10, not 10, this is 9, I believe. Yes, so we will reassemble at 9:10. So after around 10 minutes, it is 3 minutes to 10 now. We will reassemble. It is 3 minutes to 9. It is almost 9. We will reassemble at 9:10. Thank you so much.